Hello students, welcome to AppDevi's YouTube platform for class 12 physics. Today we will consider a typical problem from electricity, resistive electrical circuits. Let us see the statement of the problem. See the statement of the problem carefully. Rin and R testing are the resistances between points A and B. A and B are 2 points in the circuit. 1 and 2 respectively. R1, R2, etc. are resistances in ohm and K is a real number. Find the value of R plus K by Rn. So this is the question. This is a resistive circuit. So instead of using this symbol, we have used this symbol for resistance. So these are both same thing. So this is a infinite network sort of thing. We call this network a ladder network. Just if we draw the circuit, it is like this. This resistance is R1, this is R2, this is R3, this is R4, this is R5, this is R6, and it continues like this. In between, there may be R2n plus 1, R2n, R2n plus 2, and the network continues to infinity. So this is the network. We call this an infinite ladder network. Some of you might be familiar with this type of network. It continues to infinity and all the resistances are equal. This is another typical problem, but here it is a more general problem. This is an infinite ladder network where all the resistors are of equal value, but here all are different. R1, R2, R3, R4, etc. So Rn is the input impedance or input resistance between points A and B. This is Rin. That means if we measure the equivalent resistance between 1 and 2, it becomes Rin. Now, circuit 2 is same as circuit 1 except that all the resistances are K times that of R1, circuit 1. The first resistance is KR1, second resistance is KR2, third resistance is KR3, fourth resistance is KR4, something like that, where K is a real number. Now we have to compare, we have to find the value of Rin dashed by Rin. Okay, so this is the problem. This is a typical problem. Here is an infinite ladder network and R1, R2, R3, R4, these are all different. Okay, so how do we do that? Let us see. So if I consider this network first, we'll try to find out how Rin can be expressed for this type of network. So first consider this diagram. Here you imagine that there are only few circuit elements instead of infinite long network. Say for example, consider the network of in this part only. This part. That means it is a finite network, say for example. So it is R1, R2, R3, R4, R5, R6. Okay, now consider this AB. So in this case, let RAB be the equivalent resistance between points 1 and 2 in this side. Now, how RAB can be calculated? First, we consider these two elements, these are in series. So, equivalent resistance of this combination R5 and R6 is R5 plus R6. Now, this is in parallel with R4. So, if we consider this part of the circuit, then the equivalent resistance between this point and this point will be obviously R4 multiplied by R5 plus R6 divided by R4 plus R5 plus R6. So this is the resistance between these two points, input resistance. If I call this as 1, 2, so this is R1, you can say. Okay, so R4 and parallel combination. This is parallel combination of R4 and R5 plus R6. That's why I've written like this. Now, this R12 is in series with R3, and therefore, if I consider these 2 points as 3 and 4, so between 3 and 4, the resistance will be in this direction. This is 3, and this is 4. So, what is that? First, between these 2 points, the resistance will be R3 plus R4 into R5 plus R6 by R4 plus R5 plus R6 between these 2 points. Then it is in parallel with R2. So the resistance between 3, 4 will be this resistance is in parallel with R2. So this multiplied by R2 divided by this is R34 divided by R3 plus R4 into R5 plus R6 into R2 divided by R4 plus R5 plus R6. So let us cross check once again. R12, this is the resistance between points 1 and 2 will be R4 into R5 plus R6 by R4 plus R5 plus R6. Now this R12 and R3 are in series, and therefore R3 plus R4, and then this series combination is in parallel with R2. So therefore it is R3 plus R4 into R5 plus R6 by R4 plus R5 plus R6, which is in parallel with R2. So equivalent resistance between 3 and 4 will be this R3 plus this quantity multiplied by R2 plus all these things added together. R3 plus R2 plus R4 R5 plus R6. This is, you can call this as R2 and this as R3 to maintain the symmetry. So if I divide the denominator by numerator, then I get 1 by this quantity. When divided by the entire numerator, I get 1 by R2. And then this quantity, when this quantity R2, when it is divided by this quantity, I get 1 by R3 plus R4 into R5 plus R6 by R4 plus R5 plus R6. So R34 I can write is 1 by R2 plus 1 by R3, and if you divide the denominator by numerator, both sides. If I divide both sides, numerator and denominator, by R4 into R5 plus R6, then what I get? The first term, this term gives 1 by R4. R5 plus R6 divided by R4 plus R4 into R5 plus R6 gives 1 by R5. And R4 divided by R4 into R5 plus R6, it gives 1 by R5 plus R6. Okay, so this is R34 between these 2 points, and therefore Rin is actually series combination of R1 plus R34. So Rin or RAB in this case, which is Rin, is equal to R1 plus this much. So what if you look at the circuit, actually it is R5 plus R6 series combination, and R4, R5 plus R6 and R4, they are in parallel. So this is the 1 by this quantity is the resistance, equivalent resistance between 1 and 2. Okay, so this is like this. This is in series with R3, and when I am making a parallel combination of R2 and this these 2 points, then I get this quantity. Then reciprocal of this in series with R1 gives the input impedance. So this is the expression of this circuit. Expression of RAB, the input impedance or input resistance between AB, the equivalent resistance between points A and B can be expressed like this. Okay, now see, if I consider another circuit, so what I got, if I consider this circuit, the equivalent resistance between points A and B, or input resistance with respect to the points 1A and B, in this particular circuit is like this. This is R1 plus 1 by R2 this much. So this expression is a continued fraction type expression. Okay, now if we consider another circuit like this. Here these are K and B points. This is K R1, K times R1, this is K times R2, this is K times R3, this is K times R4, K times R5, and K times R6. Then obviously here if I call these as R dash T or R dash AB, the equivalent resistance between points AB in this particular circuit, then it can be definitely written as Rin dash RAB, R dash AB is equal to R dash in input resistance is actually KR1 plus 1 by plus okay, just multiply each resistance by K and we get the expression for R dash AB. So it is KR1 1 by KR2, this term 1 by R3 becomes KR3, 1 by R4 becomes KR4, and R5 becomes KR5, and R6 becomes KR6. Okay, now just think of this expression KRE. KRE means you have to multiply this term by K. So KRE, if I call it, so it is K times R1 and then multiply K by 1 by R2 plus 1 by R3 plus 1 by R4, 1 by R4, sorry. R5 plus R6. Remember there is a key over there. Since there is a key over there, I can replace the K and bring this K there. I can make this K 1 over there and divide it by K. So K comes here, K comes here also. So K comes here also, but this K I can bring it here and here and here. So instead, so I can write like this, multiply by K. When I'm computing KR1, KR1, then numerator will be K, but this K I'm bringing down like this. And here also I have to multiply, so KR3, and K comes here, so this K comes in here, and KR5 plus KR6. But this is what? This is this expression. So it is nothing but R dash T. Okay, so R dash T is equal to K times RE. So if RE is the equivalent resistance between AB in this circuit, and if R dash is the equivalent resistance between A and B in this circuit, then R in dash is A times R in. Okay, now this is a finite length circuit. If it is an infinitely long circuit like this, then what happens? So the resistance, input resistance or resistance between points A and B can be expressed as a continued fraction like this R1. This is the expression. If we have considered up to R6, so it is this part in the previous calculation it is missing. So R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 by 1 by R2. This is R6 is there, so this part is missing, not entire. This part is missing. So R5 plus 1 by 1 by R6 becomes R5 plus R6. Okay, now R in dash will be for the infinitely long infinite ladder. R1 will be replaced by KR1, R2 will be replaced by KR2, R3 will be replaced by KR3, R4 will be replaced by KR4, and so on. And therefore, definitely R in dash with the same logic will be K times R in. Okay. So whatever you have done, I think it is clear. So in this circuit, what will happen? If this is the input resistance or this is the resistance between equivalent resistance between A and B, and this is R dash is the equivalent resistance between A and B in circuit 2, then definitely R in dash is equal to K times R in. Okay. So this problem is very interesting problem in solving various other type problems like I will explain. See, for example, you are given a problem like this. And consider this as the infinite ladder to infinity. Okay, this is A. So, what is the value of R in, which is equivalent resistance between points A and B in this circuit? Now, take these 2 points CD. So, if we look at CD, so you can think between C and D there is an infinite ladder whose resistances are actually K times that in the circuit in with input A and B. So I can, if RE is the equivalent resistance between A and B, then and RE dash, if it is equivalent resistance between C and D, then I can definitely redraw the circuit like this. And this is, if it is RE between A and B, equivalent circuit, then between C and D, the equivalent circuit will be K times RE. If I call RE as X, then I can call this as Kx. Because if X is equivalent resistance between points A and B in this circuit, then between C and D, if we look the circuit from this cross section towards this direction, the equivalent circuit between C and D will be definitely K times X. Because this circuit, all the resistance values are multiplied by number K. So this is Kx. So this is R. So I can write the equivalent resistance between R and Kx will be R into Kx by R plus Kx. When coupled with this R, which is in series with this equivalent resistance, this has to be equal to X. Okay, R into Kx by R plus Kx plus R has to be equal to X. Or you can write R plus Kx, R square plus KRx plus KRx has to be equal to X. Or Kx square plus Rx equal to R square plus 2KRx. So this is how much? R square plus 2KRx, and this is R plus Kx. So Kx square plus Rx. So it is Kx square plus X, if I take common, X into R if I take common, then 1 minus 2K minus R square equal to 0. Okay, so solving this equation, quadratic equation in X, you can find out the value of X. So the input impedance or input resistance between the points A and B can be solved by solving this equation. Okay, so it's a quadratic equation. And you can compare this value, input resistance, with what you already know, this type of circuit. Where all resistances are equal, you can work out this type of circuit's resistance with this substituting K equal to 1 in the expression. So this is generalized ladder network, and we have seen that Rin dashed is actually K times R. This is a very important result for resistive network. Rin dash equal to K times R. So all the here Rin is the input resistance or equivalent resistance between point A and B. Here R dash T is the equivalent resistance between points A and B in this circuit, where all the resistance are K times that in the circuit 1, and it can be found. We have already shown R dash T is equal to K times R. So I hope you have understood the problem. If you have any doubt, you can revert back to us. We will try to clarify, and you can solve various type of problems once you understand the principle of this circuit. That is, Rin dash is equal to K times Rin. Okay, so thank you very much for your listening. Thank you once again.